All right, welcome back. This is going to be the capstone of our study in Chapter 6. This is actually the most challenging, which makes sense for it to be the last section, but it kind of piggybacks off of what we just did. This section is called Coordinate Proofs. Coordinate Proofs. And if you can do 6.7 pretty well, and you can go over and work with abstract ideas, this shouldn't be too hard, but it can get a little challenging for some people. The start thinking part says a rectangle has the following vertices with these locations. Show the diagonals are congruent. So we're not going to actually work through the whole entire thing, but here would be the concept. You guys know we would plot all of our points. So let's say there was a point here, a point here, a point here, and a point here, and that was a rectangle. And if we wanted to go over and show that the diagonals were congruent, we would find the distance. Let's say we call this A, B, C, and D. We would find the distance between A and C, get it down to be a single number, whether it's an actual integer or if you got down to the point where it was like radical 60 or something like that. And then if you went over and figured out the distance between here and here, you would want to show that it was the same exact number. So if it was rad 60 when you did the distance between those two, then it would be rad 60 again. The deal would be that you would get two of the points and you do the distance formula. That's the formula you want to do to show that diagonals are congruent. And then you do it with the other points. It doesn't exactly matter exactly what the number is, it's just we're looking for the fact that they are the same. If they are the same, then the diagonals are congruent. Okay? So my question then becomes, is this enough to prove that for every rectangle that the diagonals are congruent? Now, I think I've talked to you guys about this before, but basically in math, to prove something is false, it's pretty easy. You just have to show it does not work in one case. If you want to show that it is true, you have to show that it works in infinitely, actually, let me make it infinitely the other way, like this, infinitely many cases. So you might ask yourself, well, how many cases did we just show? This was one case where the rectangle had these vertices. Okay, so the question then becomes, how do we show infinitely many rectangles? So basically, what we can do is rather than using numbers which lock it into a specific example, you can use variables. And since the variables could have any value, then you're looking at infinitely many rectangles, or whatever shape you're trying to talk about. So let's continue on here. It says, when showing something is false in math, you only have to show it does not work in one case. Okay, when showing that something is true, you have to show that it works in infinitely many cases. Once again, a coordinate proof is going to be a proof using formulas and variables to show something is true. All right, so I've given you the basics of we just need to use variables rather than numbers, but I'm sure that doesn't make complete sense to you. Let me go ahead and show you the difference between a single case and infinitely many cases. Here would be a single rectangle. If I called this 0, 0, then I went up by, let's say, 3. I just picked some number, so that would be 0, 3. And then this one I went over by, let's say, 4, so it would be 4, 0. And then this point right here would be over by 4 and up by 3, 4, 3. That would be a single case. This is a specific rectangle. This is not infinitely many rectangles. Now let me show you how to make infinitely many rectangles. You can still place your rectangle strategically on here. I'll go ahead and show you. So I'm going to place it strategically so that it is starting at that location. So it is okay to have the point 0, 0 being one of them, but you don't want to use numbers for any of the other parts. Now, instead of us going up by 3 units, let's go up by a units. So it'd be 0, comma a. And since a can be any number, that could be whatever height, doesn't matter. It can even be negative, so it could be flipped upside down. But a is going to be the non-unique variable we talk about here to talk about how high the rectangle is. And over here is going to be over by, well, I've already called it a, and I don't want to say that they are the same exact length, the left side and the bottom. So let's say it went over by b units, and it did not go up at all, so it's b0. And then right here would be over by b, up by a. This is a way of showing infinitely many cases, okay? So we talked about how a could be anything and b could be anything, but no matter what number you make a and what number you make b, if you went over and let's say a was 7 and b was 9 or something like that, if you filled the a and the b's in with 7s and 9s and you graphed it, you would see it would be a rectangle. Okay, if you called that a -7 and b was 9 and put those numbers in, you would still get a rectangle. Okay. Now here's the deal. This is the trickiest part when you're talking about a coordinate proof. When setting up a figure in a coordinate proof, it is important to have good placement. What I mean by good placement is that you have to use the least number of variables possible. So once again, good placement, I just showed you one. If we went over and made our rectangle look like this, we had to invent a variable over here, so that was up by a. We had to invent another variable, which would be over by b. This was just 0, 0. And then here we didn't have to come up with a new variable because it was over by b and up by a. I was still able to use the variables we've already talked about. Another example of good placement with a rectangle could have been like this. Let's say this is over by a units and up by b units. To talk about all the other locations, I don't even have to come up with any other variables. This one is still over by a, but now it's dropping. Instead of going up positive b, it's going down b. This one over here would be to the left a units and down b units. And this one would be left a units and up b units. Notice I still only needed 2 different variables. I want to explain once again, why did I have to even have 2 variables? Why didn't I just use just a's? Because I did not want to give the point that had to be over and up the same exact amount. I wanted it to be over a certain amount and up a different amount. That way it is a rectangle, and we're not talking about a specific rectangle called a square. If you use the same variable, then you're talking about, you don't know what that number is, but you're saying it has to be the same. Like if this was AA, then if that was over by 5, it would have to be up by 5 as well. Now let me show you bad placement. Here's bad placement for a rectangle. We called this over by A and up by B. If I wanted to know where that was, I have no way of using these variables that I already have to talk about that location. So then I would have to use different variables. Over by C, up by D. And then I still wouldn't be able to use any of those variables to talk about this one, so I'd have to use other ones, E and F. And over here, I still can't use any of those variables, so I'd have to invent more. And whenever you're doing a coordinate proof, it's important to use the least number of variables possible. How do you do that? By using your logic, okay? Meaning like here, this point, if this is a rectangle, I went over by A and up by B to get to that point, then this point would also be over by A just into the negatives and up by B. So using logic and as little number of variables as possible. So most of this lesson has to do with just going over and trying to figure out locations. What do I mean by that? I mean, like, if we knew this whole entire length here was 2a units, then how much is over here and how much is over here? A and A. And since this is a square, if this is 2a units, then that's also got to be 2a units. That would be A, and that would be A. So where is this location? Over A, up by A. I do want them to be the same because it's a square. Where's that location? A, negative A, because I had to go down. How about that one? Over by A into the negatives, down by A. And then this one right here, over by A into the negatives, and up by A. So I was able to talk about a square with only one single variable. How did I know that was over by A and up by A? Because they told me the whole length was 2A. Now let's look at this. This is saying this is an isosceles triangle. They tell us that the base here is 2A units. So how much is over here and how much is over there? If it's nice and symmetric about the y-axis, A and A. So if this was over by A and didn't go up, it'd be A0. If that was over by A and didn't go up, it would be negative A0 because I had to go into the negatives. Can I somehow use the A to figure out what that is? Nope. I have to. It's going to be 0 comma something. I don't want to say it's A because I don't know it's going to be exactly the same amount that it took to get to here. So I'd have to come up with a different variable, which is, let's say, B or C. Look at more. On this one right here, it says it has a height of A and a length of 2B. Means that's B. That's B. So what's this location? How much did we go over by? B. How much did I go up or down by? Nothing. How about this one? Over by B, but into the negatives, and I didn't go up or down. So it'd be 0. What about this? Over by B, and it looks like up by A. Over by B and by A. And this one? Over by B in the other direction and up by A. Hopefully you're getting the hang of this. We're just using variables. Now this one says it's a kite. IE is 2A. So A there and A there. And then KO is B. And OT is C. So what are these locations? What's this one? To the right by C. Did it go up or down? Nope. This one right here didn't go left or right, but how much did it go down by? This one didn't go left or right, but how much did it go up by? And this one right here, how much did it go to the left? Well, into the negatives, that amount. And then it is going to be 0 because it did not go up or down. All right. Now, almost done with this. This says that parallelogram with a height of m and z is j units. Something is telling me that I wanted this to be different, but I don't think so. Let's just see if it works. So what would this location be? Over by j, up by nothing. How about this one? Over by nothing, and then how much do I go up by? M. Now I know that this one is still going to be the same height as W was, so I could say it was height of M, but I have no idea how much I went over by. So we have to come up with a new variable. Let's call it V. Now with that, this is going to be the hardest one. Well, how far over did that go by? Well, if this is V, then this is also V down here. And what did we say this was? J. So the total is going to be J plus V. And then it did not go up or down, so it's J plus V, comma 0. That would probably be the hardest one that we would do. So far, you might be saying, what in the heck are we doing? Right now, all we're talking about is how to use variables to figure out locations. Okay, we still haven't done a proof. All we've done is we've explained that placement of your figure is important and that you want to use the least number of variables as possible. And rather than talking about going over by a certain number like 4 and up by 5 and being a point 4, 5, we would say going over by A and up by B. All right. Now I want to show you how we would actually do one of these proofs. We're going to skip this stuff. And we're going to go to here. So let's say we wanted to show, let me find the easiest one because we're not going to get crazy since this is an online class. Let's do this one. Okay. Now here is how you would do a proof. We have gone over and created all of these points so that it is a rectangle. Where we have one missing, and that's just going to be up by 0. And let me put this in, up by 0 and over by the same amount that was over by A. Now this is how you would do a coordinate proof. Let's say we wanted to show that this length, I'm going to go over and white some stuff out because we're going to do this slightly different. White out. Okay. Now watch this. Let's say we wanted to show that for every rectangle, the diagonals are congruent. Now normally we would have done it in the last section by just using points with numbers. Now we're going to do the same exact process, but instead of points with numbers, we're going to do points with variables. So what formulas would I have done to show that diagonals were congruent? I would have done the distance formula. So let's do the distance formula, but now we're going to do it with variables. So watch this. Rather than getting down to the point where we have like radical 60 equals radical 60, watch what we do with variables. Square root of x2 minus x1 squared plus y2 minus y1 squared. Square root of a squared plus negative b squared. We're going to keep going until it's simplified as much as we can go. Square root of a squared, negative b times negative b is b squared. If I can make this one also into square root of a squared plus b squared, then we know that they will be the same length. x1, y1, x2, y2. Square root of a minus 0 squared plus b minus 0 squared. Square root of a squared plus b squared. Same, so congruent. That would be an example of a coordinate proof. Let's go through this step by step again. 1, we're doing the same exact stuff we did in the last section. Same formulas, same everything. 2, instead of using numbers, we are using variables. 3, the placement is important, meaning place your figure in a certain way so that you have to use the least number of variables possible. C, still just go, or number 4, just remember what you did in 6.7 and you're going to do the same exact thing. So I'm going to do one last piece. Let's say we are trying to show that the diagonals bisected one another. Diagonals bisecting one another would have been midpoints. So we're still going to do midpoints, but now we have variables instead. So let's find out what the midpoint of this is. Just add your x's together and divide by 2, and add your y's together and divide by 2. The midpoint is a over 2, b over 2. So what does the midpoint have to be of this one? Same exact thing. Let's see if we can add them together, divide by 2, and get the same midpoint, meaning they bisect one another, just like we did in 6.7. 0 plus a divided by 2, 0 plus b divided by 2. A over 2, b over 2. Since those are the same, even though they're not numbers, since they are the same, then we know that the diagonals bisect one another. This is the basically the underlying thought process of a coordinate proof. We'll be talking about this a lot more in class, so come with questions. If you don't understand why I used variables, ask me in class. Go over all this stuff. We could talk about how we would view it if we were trying to find out that the slope of this was the same as the slope of that, or that they were parallel. You would use the slope formula between these points and the slope formula between those points, and you would show they were the same. Instead of the slopes being like 1/2, 1/2, you might have a slope of a over b and a slope of a over b. All right, come to class with questions. Thanks for watching.